so you're the...
Most excellent agent we've ever seen.
Yes, most excellent agent we've ever seen. Thank you.
Thank you.
Now, I wasn't able to get an exact location, but I did learn that Dr. Evil has moved to a new lair outside of Tokyo, Japan. By the way, I realized that I have a large mole on my face. Where? What? Where's that mole? I didn't see one. I also realized the irony that I am myself a mole. No one would make that connection.
Anyway, well done, old chap. Jolly good work.
Yes, nice to mole you. Meet you. Nice to meet you, mole. Don't say mole.
Stop.
I said mole.
Stop.
Bye, mole. Mole. Mole.
Oh, shut up!
Molly, 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 Molly.
Okay, so you probably guessed by now that we're going to talk about the mole. Well, we're not going to talk about the mole on your chin, or a mole cricket, or whack-a-mole, or mole sauce, not even guacamole, and not even the cute, adorable little mole. No, we're going to talk about a mole as a measurement that we use in chemistry. We're going to compare this to a yard, a dozen, a case, and a pint. Those are all types of measurements. Well, a yard is 36 inches. A dozen could be 12 donuts, a dozen eggs, a dozen golf balls. It just means 12 of something. A case of something means 24. It could be 24 cans of soda. It could be 24 cans of dog food. A pint is 2 cups. Okay, a mole is just a measurement we use in chemistry. And it's 6.02 times 10 to the 23rd, and it could be atoms, it could be molecules, it could be anything. It's just 6.02 times 10 to the 23rd. Things.
Wait, no, don't we already have a way of measuring elements? And you're right, we do. The real coin of the realm when it comes to measuring stuff in chemistry is relative atomic mass, the average atomic mass of all of the naturally occurring isotopes of a given element. So, for example, all of the natural carbon on Earth occurs as one of 3 and only 3 isotopes, C12, C13, and C14. They all have 6 protons, but the number of neutrons vary. And these isotopes show up on our planet in totally different proportions. So the relative atomic mass of carbon is a weighted average of these 3 masses, which comes out to 12.01. But 12.01 what? Well, remember when we were talking about units of measurement, we're talking about arbitrary talk. Most units, except for the ones that we use to measure time, aren't based on any real objective value. We just pick a unit, like the kilogram, and we agree for a standard on what a kilogram is, and then we run with it. The same goes for atomic mass. We measure atomic mass in atomic mass units. We made them up, and the value for a single AMU is, bear with me now, 1/12 of the mass of an atom of carbon-12. Why? Funny story. Until the mid-1800s, chemists in different parts of the world used different yardsticks for measuring elements. One of the most intuitive, and therefore most common, was to use the smallest, simplest element, hydrogen, as a baseline. But in the 1850s, some chemists, led by German Wilhelm Ostwald, proposed using oxygen instead. They preferred oxygen mainly because it combined readily with so many other elements, so they figured it would be easier to determine the weights of lots of compounds. So a bunch of guys stroked their beards, agonized over this for years, until in 1903 they decided that atomic weight, as it was called, should be measured in 1/16 of an oxygen atom. Until, in 1912, isotopes were discovered and chemists realized that you can't talk about an element like it's all the same thing. It turned out there was an oxygen 16 and an oxygen 17 and an oxygen 18. And suddenly, everyone was walking around like, I don't know how much this stuff weighs anymore. This was so crazily disruptive that it took another 50 years of strokey beard meetings for everyone to decide to use another standard, carbon-12. Like oxygen, carbon is common and kind of promiscuous when it comes to what it bonds with, and since it has 12 protons and neutrons, the mass of other similar elements could easily be expressed as some fraction of it. So, since 1961, science has pegged 1 AMU as 1/12 of an atom of carbon-12, which means that carbon has a relative atomic mass of 12.01 AMU, oxygen 16 AMU, and hydrogen 1.008 AMU. So that's how we weigh atoms. But none of this solves my tea sweetening problem. Like, I don't know how many AMUs of these molecules together are gonna make this taste good to me, or how many molecules of sugar I can consume while maintaining my slim yet robust physique. This doesn't happen by itself, you know. In order to make these calculations and predict reactions, I first need to be able to convert the atomic mass of this sugar into a standard amount of substance. Not weight, not volume, just purely objective amount of stuff. You heard me. Stuff. That, my friends, is what moles are for. Not those moles. Those are nice-looking moles. A mole is arguably the most important unit in all of chemistry because it allows us to express a chemical's atomic mass in terms of grams. And to define what a mole is, no matter what it's a mole of, we use our old standby carbon-12. There are 6.022 times 10 to the 23rd atoms in 12 grams of carbon-12, and by definition, that number of anything is a mole of that thing. That's a lot, and it is known as Avogadro's number, one of the most important constants in chemistry, and although Avogadro isn't the one who arrived at this number, it's named in his honor because he used this basic principle of comparing amounts of substances to first weigh atoms and molecules. So there are this many carbon atoms in a mole of carbon-12, and there are the same number of anything in a mole of anything else. Like a dozen roses is 12 roses, but a mole of roses is 6.022 times 10 to the 23rd roses, which would be enough roses to cover the surface of the earth quite deep. A mole of sand would be 6.022 times 10 to the 23rd grains of sand, and if they were each 1 millimeter long, a mole of them would stretch 100 quadrillion kilometers. So you get the picture? It's a big number. But in chemistry, the thing to remember is this. A mole of any element contains 6.022 times 10 to the 23rd atoms of that element, no matter what. This is what lets us translate numbers of atoms into grams.
Okay, well, as he just said, a mole is a very large number, but let's get some perspective on exactly how large a number that is. Let's talk about money. If you were very lucky over the holidays, you may have received $100 for Christmas. Or your parents may be making a car payment that's about $800. Or they could be making a mortgage payment that's, say, $1,000. They may have purchased a home that's worth $250,000, which is a nice home. Or if you want to be a millionaire, you're going to need to have $1 million. And the national debt is that much. I don't even know how to say that. But still, 6.022 times 10 to the 23rd is much more than the national debt. If you had this much money, you could buy anything you wanted and never run out of money in your lifetime. So that is a huge number. Now, why do we have to have such a large number like this? Well, it's because the atom is so incredibly small. To even be able to talk about atoms, we need to talk about this many atoms make up a certain amount of substance. For example, if you had this many atoms, 6.022 times 10 to the 23rd of hydrogen, you would have just 1 gram of hydrogen. And what do we know that weighs 1 gram? A small paperclip. Now that's a lot of atoms to have that small of a mass. Well, so how are we going to use this in chemistry? Well, we're going to use this to figure out problems. Like we'll be given moles or we'll be given grams, and we'll have to convert back and forth. So here's a simple problem. How many moles are in 40 grams of water? So if you had 40 grams of water, how many moles would that be? Well, to first set this up, we take what's given, and 40 grams of water is what's given to us, and we're going to put that in our picket fence in the top left corner. Now we're going to put this over 1, and we want to get rid of the grams of H2O, and we want to find out how many moles that is. Well, in order to do this, we're going to have to find out something about water, and that's how many grams are in a mole of water. And we do that by breaking water apart, H2O, into its elements. And if we look on the periodic table, we can see, and look at hydrogen, we can see that the average atomic mass of hydrogen is 1.008. So if we round that to the nearest 10th place, we're going to get 2.0 because there's 2 moles of hydrogen in a mole of water. And that's where that 2 comes from. So we have to take that 1.0 and double it, or multiply it by 2, and get 2.0 grams per mole of hydrogen. And then we do the same thing with oxygen. If we look up oxygen on the periodic table, we see that the average atomic mass of oxygen is 15.999. And if we round that to the nearest 10th, we're going to get 16.0 grams of oxygen per mole. Now we add our hydrogen, which is 2.0, with our oxygen, which is 16, and we're going to get 18.0 grams per mole. That's how many grams are in 1 mole of water. So we're going to substitute that in on the bottom because we want to get rid of grams, and on the top we're going to have 1 mole. So if we do our cross cancellation and get rid of that unit, we're going to be left with moles. And then if we do the math here, if we multiply across the top and multiply across the bottom and then divide 40 by 18, we're going to come up with 2.22 moles of water. So 40 grams is 2.22 moles of water. Well, we can also do another problem where we talk about how many atoms are in that 2.22 moles of water. So in that 40 grams of water, exactly how many atoms is that going to be? Well, we set it up the very exact same way. So we take what's given and we put it in our upper left corner of our picket fence, and we put it over 1. And we want to get rid of moles of water, and we want to convert it to particles or molecules. So we just say particles. So we're going to take 1 mole and we're going to put it on bottom, because the conversion factor is 1 mole of any substance is 6.02 times 10 to the 23rd particles. And that's what we just learned what the mole was. So 1 mole is 6.02 times 10 to the 23rd particles. And this is called Avogadro's number. So please write that down. Avogadro's number. Okay, so moles cancels moles, and we're left with particles. And when we do the math, 2.22 times 6.02 times 10 to the 23rd, we're going to get 1.35 times 10 to the 24th particles. Okay, that says atoms there, but it really should say particles or molecules. We're going to use these conversions in chemistry this week, converting between grams to moles and moles to particles.